right, let's take a look at this lesson. So we're going to be looking at critical points and intervals of increasing and decreasing. And yeah, some of it we might be a little bit familiar with, but we're going to go through it formally now during this lesson. So we're going to start with intervals of increase and decrease. So what do we mean when a function is increasing or decreasing? So the precise definition that we're going to look at is we can say that a function is increasing if on an interval, so from a to b, which is what we have in our diagram too, if on that interval any y values that you have, or values of the function, if you have a value that's bigger than another value, that must have occurred when the x value is bigger than the other value. Okay. It's a weird way to put it, but essentially what it's saying is that if you're looking at 2 points on your function over here, on the graph of the function, if the point is above the other point, then it must have been further along the function. Or another way of thinking of it is that the slope of the tangent, if we're looking at it, we're just going upwards. So the slope of the tangent is positive. So it's an odd, like when you first read the definition, it feels odd, but that's all it's really trying to say is that you're just going upwards. So those y values must be increasing as those x values increase. So as x increases, the y values increase. All right. And basically the opposite is going to be a decreasing interval. So if it's decreasing a function on an interval, it just means it's going downwards. And when we're talking about like going downwards, going upwards, we're always reading left to right. So decreasing, going down from left to right. All right, so let's actually take a look at a graph and just identify these regions of increasing and decreasing. So we have this graph here. It's got a whole bunch of parts, some kind of piecewise function. And what we want to do is we want to figure out where, it's increasing, decreasing, or constant. So we'll take a look at this first chunk, and we'll see to begin with that, you're just going, again, going from left to right, going downwards, 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 and eventually you hit some minimum there. So we could say that the function there is decreasing. And continue along, we're going up and then going down. Okay, for this next part, you're going straight across. So you're not going up or down. And that's what we just call constant. And the last part, we're going upwards. So now let's take how we've read that graph from left to right, and let's translate that into intervals of increasing and decreasing. So we'll just go decreasing first, then increasing, and then constant. So taking a look at these, what we're going to have is we're decreasing from, I'll use our interval notation, x is an element of, well, the graph is going to go continuously to the left, so we can say we're starting at negative infinity, and eventually it seems like we hit that minimum at -4. We're not going to include -4, we're excluding that because that's going to basically be where we have, let's say, slope 0. So it's not going up or down at that point. And that's not the only part where it's going down. We can also see at -2. So I'll union that with -2 to 0. So we have those two portions. Increasing. So looking at increasing where we're going up, at -4, again, with all these parts, I'm generally going to be using open intervals because we're not including those points where it's changing from going up or down to up. So -4 to -2. And then at the end there, you can see it starts at 4 and goes up towards 7. And the graph doesn't have an arrow here. It's just a dot, so we're just stopping there. And the constant part. So that's the part where it wasn't going up or down. So we're going to go from 2, or sorry, not 2, that's the y value. We're going to go from 0, that's where the x value is, all the way to 4. And there we have it. Those are the intervals where it's increasing, decreasing, or constant. All right. And yeah, how do we actually test for this? If we're not given the graph, we can't just look left to right, see what's happening. Well, kind of mentioned it a little bit before. We're looking at slopes of tangents, which means we're looking at the derivative. So the derivative will tell us if it's going up, if it's going down, or if it's constant. And so if the derivative is positive, which is what that first one is saying in an interval, then we can say that f of x is increasing over that interval. If the slope is negative, well, then we can say that you're going down, decreasing. The last point, so if f prime of x is equal to 0, well, there's two things. It could either be the constant like we had up above, but more importantly, it could be a transition point where we're going from increasing to decreasing or decreasing to increasing. And this means there may be a maximum, really I should say local maximum or minimum at that particular point. And we'll see how do we figure that out. That's what we're going to go through later. And yeah, just remember that f prime of x, this derivative, is the slope of the tangent, so it's telling us what direction that graph is going in. So let's figure out some intervals now just based off a function. So we're looking at f of x equals to negative 2x cubed over 3 plus x squared plus 12x minus 1. So we just want to figure out the derivative, which in this case is just going to be negative 2x cubed, the 3's cancel out, plus 2x plus 12. All right. Oh, I should turn that cubed into a squared, negative 2x squared. And then, well, let's factor out. So since we want to figure out where we're increasing and decreasing, what we're going to do is we're going to find kind of those points where the transition points are. And we're going to do that by finding the zeros, and then we can basically test in between the zeros. So first of all, that means we have to factor this. So x squared minus x minus 6, and that's going to turn into x minus 3, x plus 2. So again, we're finding transition points, I'll call them for now. By finding zeros. Okay. So we have x is equal to 3 or x equals negative 2 when f prime of x equals 0. So what we're going to do now is let's do basically a number line and just test some values on this number line. So we're looking at negative 2 and 3. Doesn't really matter what numbers as long as they're in the interval. And really all I'm looking for is the sign. So it doesn't matter exactly what this function actually values to. So what I always like to do is I just, look at the sign of all the different parts. So if I'm plugging in negative 4, well, what's f prime of x going to equal? Well, we're going to have a negative in front. So I'm just going to put a negative sign in front. That's the negative 2. Negative 4 minus 3 is negative. Negative 4 plus 2 is negative. 3 negatives together make a negative. Plugging in 0, you still have that negative in front. 0 minus 3 is still negative. 0 plus 2 now is positive. So that is going to be positive. And then lastly, if you put in some number bigger than 3, let's say 5, you still have that negative in front. Positive and a positive make it a negative in the end. And this now tells us where our derivative is negative, where our derivative is positive, thus the intervals of increase and decrease. So we can say that the function is decreasing for x from negative infinity to negative 2, and from 3 to positive infinity. And it's increasing from x, basically between those two, negative 2 to 3. And then we have those special transition points at negative 2 and 3 specifically themselves. All right. So there we go. It's just a matter of taking derivative, finding some zeros. But we do have to be careful because not all our functions are going to be continuous functions. And there are going to be situations where we do need to pay attention to, let's say, discontinuities or things like asymptotes, or if you have a hole, something like that. So if we take a look at this function here, let's look at this particular area right here. I'm just going to draw in an asymptote there. So in that area, our function itself, you can see it's definitely going down as you approach that area. But then, remember, since we're reading graphs from left to right, if you go past that asymptote, going from left to right, we're going upwards. So actually what's happening here is we're going from decreasing on the left to increasing on the right. There was no minimum or maximum there. So this just happened at an asymptote. And that's really what we have to check for as well sometimes is if we have an asymptote, if we have a hole, double check that particular value, or around those values, I should say. Can't check that actual value, but around those values you can check, is it positive or negative as well. So check vertical asymptotes and holes. Because we could transition from positive to negative in our derivative at those points. Okay, so these points that I was calling like the transition points where it's changing from decreasing to increasing, we do have a special name for that. We call them critical points. And we actually have a whole bunch of names. Sometimes when we're looking at a graph, let's look at the graph to the right there. Those turning points you might have referred to them as. We can also call them local maximum and minimums. That's what I've been referring to them as. You can also call them relative maximum and minimums. Again, these are all just similar terms, but just different ways of calling it. Or the local extrema. So the extreme points are those maximum and minimums. And so yeah, when we're talking about a critical point, essentially it's any point where the derivative is equal to 0. What's important though is that if the derivative is equal to 0, it may not actually be a local maximum or minimum. And here's a quick little example just on the page here that illustrates this. So if we're looking at the function f of x equal to x cubed, we know what it looks like. We have the graph there. It's just the one where it kind of curves as you get towards the origin and goes back up. We quickly do the derivative of that. Well, that's just 3x squared. And well, x equal to 0 is 0 there. But if we take a look at our graph, well, that point at 0 is not a max or a min. So that's why I have to say a critical point where you have a 0 could be a max or a min, but does not have to be. So be careful of that. We're going to have to test things out to make sure what our maximums and minimums are. And we can do that with this thing called the first derivative test. So essentially it's going to involve the first derivative. What we do is we first of all figure out where are those zeros? Where are those critical points? That's the first thing. So we set y prime equal to 0 and solve for x. Then once we have those points, we can check what's happening to the derivative. Is it going from positive to negative as you go around those points, or from negative to positive? And that will tell us if it has a local maximum or a local minimum. And what I always like to do is just do a quick little sketch. Positive means it's going upwards. Negative means it's going downwards. What did I just draw? I drew a little curve that's going up and down, which looks like a little maximum there. If you do it in the other order, though, if you go down first and then upwards. Well, I just drew like a little downwards curve where you have a minimum. And then there's the case where maybe the sign doesn't change, which is like that x cubed graph, where it just actually keeps maybe going upwards. So that would not be a maximum or a minimum. Okay, so let's put this to use. So we want to find the critical points of this, in this case, cubic function. And then we'll classify those points. So a quick little derivative here. I should probably do the derivative correctly. 6x squared plus 6x. We'll factor this. And our zeros are x equal to 0 or x equal to -1. So what I'll do is set up a number line, -1 and 0. Again, I'm just putting some random numbers in here that are in these intervals. Doesn't really matter what specific numbers you use, because all we're looking at are the signs. We're looking at not the second derivative, the first derivative. What happens if you plug in -2? Well, you will have a negative times a negative, which is just a positive. If you plug in -0.5, 6 times -0.5 is negative. -0.5 plus 1 is positive. So that's equal to a negative value. And lastly, some big number, let's say 2. You'll have 6 times 2 is positive. 2 plus 1, positive. 2 positive, well, becomes positive. All right, so we've got critical points. X equal to -1, x equal to 0, and we want to classify these using that first derivative test. So now let's look at our derivatives. So we have a positive derivative to the left of -1, which means we're going upwards, and then it's going downwards. Well, look at what I just drew. I just drew kind of a curve that would be going like that, which would be a maximum. So what I can say at -1, it is a local max. And continuing on, we're going downwards, and then at 0, we're going to go upwards afterwards. So it looks something like that, which is a minimum. So it is a local minimum. So I always find just like a quick little sketch like that can really help illustrate and make that first derivative test a lot easier to remember, rather than just trying to memorize a bunch of different cases. All right, let's continue onwards. All right, I'd suggest pause the video here. Try this one out yourself first. I'll go through it right now, though. So we've got f of x equals to 2x minus 1, x plus 1. So I'll just quickly go through the derivative. So derivative of the numerator times the denominator. So we're using quotient rule here. So it's going to be 2 times x plus 1 minus, because it's quotient rule, derivative of the denominator, which is just 1, times 2x minus 1, all over x plus 1 squared. Let's clean up that numerator. We're going to have 2x plus 2 minus 2x plus 1. Careful of that double negative. X plus 1 squared. And what do we get? We get, well, the x's cancel out. 2x minus 2x. X plus 1 squared. All right. So in this case, if we set this function equal to 0, well, you'd set the numerator equal to 0, so no zeros. However, we have to remember a critical point, or where we have to check for like intervals of increasing and decreasing, is not just where the derivative is equal to 0. We also need to check vertical asymptotes and holes. So in this case, x equal to -1 is a vertical asymptote. But because it's a vertical asymptote, you're not going to have an actual point there. So we can't classify it as a local minimum or maximum. But we could still check left and right of that if it's increasing or decreasing. So plug in some number smaller than -1, some number bigger than -1. Into the derivative, that is, let's say. And if you do that, well, you're going to have 3 over something squared, which is just positive. 0 over something squared. Or sorry, 3 over another thing squared. Again, the square on the new denominator makes this always positive. So it's always increasing. And no max/min. All right. Let's put some of these definitions and now let's think about what they look like as a graph. So if we want to graph something that has these conditions, try that out. So we're going to look at something that has a first derivative greater than 0. So it's positive, which means it's increasing on that interval. We also want to have local extrema at -2 and 4, which is actually the ends of that interval. So that's important to note. And we have a critical point at -5. So let's just start with the local extrema and the increasing interval. So what that's going to mean, if we're increasing from -2 to 4, it doesn't really matter where I start. So I'm just going to start down here and just go up. We could draw it as a line. We could draw it as a curve. Doesn't matter. We're going to go up to there. All right. So there I have fulfilled that first criteria. These are local extrema. So the left one I'm going to make a minimum. That's the only thing we can do. And the right one I'm going to make a maximum. We're kind of forced into what kind of extrema it must be. And so there we go. And another critical point at x equal to -5. So this is where we have to think back to that x cubed example. X cubed had a critical point because the function was basically flattening out there. So where we have slope 0, but it did not lead to a local max or min. So that's what we're going to do. We're going to approach -5. I'm just going to draw a point here at -5. We're going to flatten out like it's a... Here, we're just going to try to make that a little neater. And we've got that. On the right-hand side, just continue the graph with an arrow. So don't forget your arrows on your graphs. So we've got the critical point. We've got the local min, local max. And again, we got that not right away, but we got that from the fact that the graph was increasing. And note that it's not increasing anywhere else as well. It's always decreasing in those other regions. All right. One last example. So we've got the function ax to the 4 plus bx squared plus cx plus d. Okay, a whole lot of variables there. And we know that it has a local max and a local min at 1, -8, and 0, -6. So we've got some points. What we can do if we want to figure out these coefficients, plug in the points into the function. So f of 0, well, it's just going to be 0 plus 0 plus 0, d basically. And we know that that is equal to 6, or -6. So d must be -6. So I'm going to rewrite the function now with that in mind. So we now have -6 at the end. All right, and let's plug in the other point, -1, -8. So plug in f of 1, which is going to be a plus b plus c minus 6, and that's negative 8. I'm just going to move the 6 over just to make things a little nicer. Okay, so that's our first pieces of information, just plugging in points, the 2 points we're given. All right, the next thing we want to make use of is the fact that we know that not only are these points, but they're local maximum and minimums. So how we can make use of that is that a local max or min, well, we know it's a critical point. And so the derivative equals 0 at those points. So if we calculate the derivative, plug in our points, see what information we can get. So f prime of x, sure, there's variables, but just leave them like that. So it's going to be 4ax cubed plus 2bx plus c, and well, d disappears. All right, and let's plug in some points. So we have our local minimum at, or maximum, I should say, at 0, negative 6. So what do we know? So at x equal to 0, local max, so f prime of 0 is equal to 0. So that's where we have to be careful. We're not plugging in the y value of the point. Since it's the derivative, the value that we're setting it equal to is, well, 0. So f prime of 0 is just going to be, well, c, and that's just equal to 0. So c equals 0. So therefore, now let's rewrite our function. F of x is equal to 4ax cubed. Oh, sorry, that's the derivative part. It's that. And let's continue onwards. So we have f prime of x equal to that. And f prime of 1 is going to be equal to 0 again, but let's plug in 1. So it's going to be 4a x cubed plus 2b plus c, but we know that c is equal to 0. And that's equal to 0. So if 0 is equal to 4a plus 2b, I'm going to call this equation 1. I realized I made a teeny mistake. It's going to be a 2b, not a b there. We'll label the equations 1 and 2. We're going to use elimination, so we have, I'll just rewrite the equations. 4a plus 2b equal to 0. That's equation 1. And equation 2, we can see 2 has a c in there, but that's just going to disappear. So it's got a and b. I'm just going to double equation 2. So 2 times equation 2. And we're going to get 2a plus 2b is equal to negative 4. Okay, let's use elimination. I've kind of stacked up the equations here already. We're going to do 1 minus double 2. We could have called it equation 3, but too late for that. And we're going to get just 2a is equal to negative 4. And by subtraction, that should be positive 4, actually. Careful about your double negatives. And so a is equal to 2. Sub that back into your equations, whichever one you want. I'll just sub it back into equation 1. Actually, probably equation 2 would have been easier, but that's all right. 4 times 2, it's all pretty simple. Equal to 0. So 2b is equal to negative 8, or 8, or b is equal to negative 4. And so therefore, our function is equal to 2x to the 4 minus 4x squared minus 6. And we were able to get that by using both the 2 points and recognizing that they were local minimums and maximums, so using their derivatives.